Good morning, class. Today we're going to be talking about what perhaps is one of my personal favorite topics in calculus, and what perhaps is one of the most influential and important topics in this subject, and that is the fundamental theorem of calculus. Now, I know it's been a while since we last covered this topic, so I'm going to give you guys a minute, talk to your partner next to you, see if you can remember what is the fundamental theorem of calculus. Give you guys a minute. Okay, by a raise of hands, can anyone tell me what is the fundamental theorem of calculus? Okay, so before we jump into the lecture, I would like to talk just a little bit about the history of this topic, as it was very revolutionary to both physics and mathematics, and it really made us change the way we see the world. So before the discovery of the fundamental theorem of calculus, there were only two other ways that we had available to calculate the area underneath a curve, and by that I simply mean literally calculating the area underneath a curve or a function. Let's say I'm trying to calculate the area underneath the function in a fixed interval a and b. The only two ways that we had available to calculate it were Riemann sums and geometric area formulas. Now, the problem with these methods is that they were extremely cumbersome, meaning that they were very complex and required a lot of work. However, back in the late 1600s, early 1700s, Isaac Newton and Gottfried Wilhelm were able to discover the relationship, or that there was a relationship between integration and differentiation. And that relationship, we now call it the fundamental theorem of calculus. Now, to have a general idea of what the fundamental theorem of calculus is used for, just remember that this theorem is used to easily calculate the exact area underneath the curve, just of how we kind of saw it in the example I provided. Now, for this lecture, I'm going to divide it into two equal parts. Now, for part one, it is very important to remember that integration is the inverse opposite operation of differentiation, kind of like how division is the inverse operation of multiplication, and addition is the inverse operation of subtraction. Well, integration is the inverse operation of differentiation. Now, to put this into more mathematical terms, we could say that if, and I'm going to write it big here, if a function, any function, in this case, f of x, is continued on the interval a to b, and the function capital f of x, and capital F of x is simply just another way to say the integral or the antiderivative, and the function capital F of x is defined by capital F of x equals integral of a is simply just a constant, x of the function ft dt, then the derivative of capital F of x, or the derivative of the integral, is going to equal the original function. And that's all you have to know for part one. So moving on to part two. Part two is just as simple as part one, and it simply states that if we're trying to evaluate the integral at a specific point, meaning this is a definite integral because we're using a specific point a and b of the function f of x with respect to x, then this is going to equal the antiderivative of f of x evaluated at that same point. And now, to solve for this, we're simply going to do the antiderivative of b minus the antiderivative of a. Pretty simple. So let's do a practice problem together. So here we have the derivative of from 1 to 3 of 1 over x dx. Now, following the notation, we could write that this is equal to, well, we know that the antiderivative of 1 over x is simply the natural log, so ln. So it would be ln of x from 3 to 1. And now following, according to this, we would have to put ln of 3 minus ln of 1. And after putting it in the calculator, we get that this equals about 1.099, if I'm not mistaken. And that's how you use the fundamental theorem of calculus. Now, to end off lecture, I'm gonna leave you guys off with this really simple problem here. And it simply says capital H of x equals x squared times the derivative from x to 3 of cos t squared dt. Pretty simple. If you guys can solve this, that's extra credit on your final. Now leave a comment down below if you're able to guess which teacher I'm impersonating. And yeah, that's it. Peace out.